All right. I guess we should maybe start. I'm sort of very skewed distribution of people today. Although you're all sitting in your normal places, it's sort of strange that there's no one in the bigger block of seats here. Yeah. So let's see. Here's what we're up to today. So I guess maybe you've had a read through that. We're going to talk about viscous flows, and I guess before we do that, I wanted to say a couple things. One, uh, sorry about getting the video up a bit late from this past week. I guess it doesn't really affect you folks since you were here for the live recording of it. But yeah, I don't know. It just didn't get it up until later in the week. So sorry about that. And otherwise, how are things going with this exercise 11? 10? I think 11 today, yeah? Going all right? Mostly? No? Okay, that's good news. So if you're having issues like the past weeks, we can deal with some of that stuff once we finish up with the lesson today. But as is the case for the past several weeks, we're going to start with a little lecture about ice and rock as viscous materials and learn a little bit about how to model flow of materials that behave in a viscous manner. And after the lecture part, then we'll take a look at exercise number 12, which is going to focus on flow of ice, so looking at kind of how glaciers behave, and then you'll be free to start working on things. So we can start maybe here with what our goals are for today, and that's basically to introduce the basic relationship for how viscous fluids flow. This is maybe not quite the same as the last 2 weeks because we're not introducing a specific equation. It's not like the diffusion or advection equation, but rather some set of equations for how viscous fluids behave. And we'll take a look at two, I guess, end-member types of viscous flows, and you'll see what that means. But these are two ways in which fluids flow when confined in a channel, and we'll also see some examples of what that means in terms of geological materials. And then we'll, at the end, talk a little bit about the effects of temperature and other nonlinear effects for how fluids flow in a viscous way before we see a little bit about ice and then transition to the exercise. To motivate things, though, it's good to take a look at some examples. And here we have one nice example of a viscous fluid, and that is ice. And whether you call this solid or fluid probably depends on the time scale a bit. But as geoscientists, we can think of ice as a fluid. And in the case of things like alpine glaciers, the ice, or really the snow that accumulates up at high elevations, is compacted into ice and begins to flow downhill under its weight once the thickness of the ice gets big enough. And I think this photo is kind of a nice example because you can almost see the shape of the fluid sort of flowing around different features in the bedrock, and looks quite like something, if you poured a very viscous fluid into this valley, it would sort of flow in exactly the same way. But over human timescales, it's a little bit hard to observe. At least like during a day, you might not see flow of ice. But ice is one of the fluids that flows at relatively high rates, and so even over a year, you can see meters of movement of glaciers. And so it's a nice thing to be able to study how ice behaves, to look at examples like this from Alaska and the U.S. Another example that's probably more familiar is glacial-isostatic adjustment, or post-glacial rebound, or whatever you want to call it. But the essential idea is that if we start with some land surface here before glaciation and put a bunch of ice on top of it, the load of the ice causes the surface of the Earth to subside, and that subsidence happens because the ice is thick enough to be a significant load, and it displaces material beneath it. In this case, it's the mantle that's pushed out of the way when the ice is subsiding. So the crust in the lithosphere flex down and displace the asthenosphere beneath it. After the glacial period, when the ice is removed, you're left with a surface that looks like this, that's out of equilibrium with its isostatic position. So if it was like this initially, and let's say it hasn't been modified significantly by the ice itself, but simply just pushed down, when the ice is gone, the surface is now depressed where it was previously, sitting above this dashed line. And so, of course, it wants to return to its equilibrium state. And the reason it relates to viscous flow is because the rate at which it can return to its original state depends on the viscosity of the mantle. So this is, in fact, one of the ways in which we can measure the viscosity of the mantle is by looking at rates of postglacial uplift. And here's a little picture from the newspaper showing rates of postglacial uplift around the Gulf of Bothnia. And I think there's even rates of up to 10 millimeters a year observed there. And that's actually, as a geological rate, quite fast. If you extrapolate that to millions of years, that's 10 kilometers of uplift in a million years. So it's quite, might not seem that exciting to the average person on the street, but it has important implications for where towns are located, because places that were on the coast before are no longer on the coast. Maybe not over our lifetime, but over a few generations. This is a process that does affect people living here, and there's maybe 60 meters or so of uplift left to go before we're back to equilibrium, and that may still then put some of these places that are currently coastal in a position of being well inland from the coast. So it'll take a little while for that to happen, though. It's an exponential uplift, and well, it's going to take some time still before the last bit of uplift occurs. So anyway, those are a couple examples of the idea of viscous flow, and in order to talk about it in any further detail, we do have to talk a little bit about some definitions of things like a fluid. And if we want to talk about fluids, well, we're talking about something that will flow when you apply a stress to it. So for most purposes, if I push down on the desk here, it doesn't move in response to me applying a stress to it, because it's not behaving like a fluid, at least not over this time scale. And probably if I guess maybe with the metal legs, if I pushed for long enough, you could eventually start to see the metal start to deform and flow a little bit, but it's not going to flow very quickly. But if you compare that to other things, if you take honey or some other substance, or toothpaste in the toothpaste tube, you squeeze on the tube and it flows out of the open end of the toothpaste tube when you apply the stress. So that's a basic definition of a fluid, and with fluids, deformation is continuous. So when you start to deform it, it's not necessarily continuous in time so much as continuous in space. So if you take some cake batter or something, if you mix it, everywhere that it's being moved is going to deform. It's not like it sort of breaks into little places that split into like faults or something like that. And in terms of a mathematical definition, we can say here that the stress that you apply is proportional to the strain rate. And if you want to think about that in terms that are maybe more familiar, if you're not that comfortable with stresses and strain rates, stress is basically a force, so kind of a push or a pull on the material, and the strain rate is how quickly it would deform. And by saying these things are proportional to one another, that's what the little symbol is here, it just means that the bigger force you apply, the more quickly the material will deform. And that probably makes sense. I mean, if you take the toothpaste tube example, it doesn't come out of the end of the tube very quickly if you just push on it lightly with one finger, but if you were to stomp on it or something, it will flow much more quickly. And the same thing's true, that if you deform the fluid more quickly, it requires more force to do that. So that's the relationship between those two things. And that's our basic starting point. We can now talk about that proportionality constant. So like we had that little symbol in there for saying the two things are proportional. We had stress over here represented with tau for shear stress in this case, and being related to the strain rate, which we just represent as du dz, where u would be some position or some displacement divided by some distance. And the way in which the two things are related for a case where this is constant is by this thing called viscosity or dynamic viscosity, but most people just call that the viscosity of the material. And that's with the Greek letter eta. And the units are kind of weird. It's Pascal seconds, and I don't really still have a good example of what a Pascal second means, but that's just the units of viscosity. We've got stress that's in pascals. We've got a strain rate, which is going to be in per second. And so if you want to get pascals equal to pascals, then you need to have units of Pascal seconds for viscosity. But the key thing is to think about viscosity like a resistance to flow. So the higher the viscosity is, the more resistant it is to flowing. And that's where this little kind of example on the left side here, this animation, is sort of useful. In the top you've got a low viscosity fluid, and in the bottom you've got a high viscosity fluid, and I'll click and the thing will come to life and you'll be able to see the difference. So low viscosity fluid flows easily. So this is more or less like water in the top being poured in, and you can see it kind of splashing and very easily sloshing around in there and flowing. Whereas the other stuff would be like, I don't know, something like toothpaste, or I thought of this silly example earlier of like, Softies kind of ice cream on a hot day that you sort of pour it out and it starts to melt and ooze, and it doesn't flow as easily as the water-like material above. So it gives you some idea of what low and high viscosities are. In terms of absolute values, compared to rock, these would both be extremely low viscosity. If rock deformed at these kind of rates, we wouldn't be able to stand on the surface of the Earth because we'd simply, well, I guess we are more buoyant, but if you applied significant forces there, the surface of the Earth would just slosh underneath your feet. That wouldn't be ideal. So anyway, that's the concept here of high and low viscosity. There are other things here, like the bulk viscosity, kinematic viscosity. If you don't know what those mean, don't worry. They're just other ways to measure the fluid's resistance to deformation. And here's a few values in the table that kind of gives you some idea of what viscosity means. So water is probably the thing we're most familiar with, has a viscosity of 10 to the minus 3 Pascal seconds. And something like honey would be 4 orders of magnitude higher. Air is 2 orders of magnitude lower. So you might not really think of air as being a fluid, but when you move your hand around, it does move with your hand, and it just doesn't take very much force to get the air to move. If you do the same thing in water, it takes more force, and if you imagine being in honey doing the same thing, it would take significantly more force to move around. Ice has a viscosity closer to 10 to the 10 Pascal seconds, and that's why it more or less holds its shape. When you put an ice cube on the table, I mean, it will start to melt, but it doesn't start to sort of flow. If you kept it cold and put the ice there, it would eventually start to flow, but it's going to take a while to be able to see that. And then you've got some other examples of geological materials like basaltic lava, which has a quite low viscosity. High temperature flows pretty easily, whereas rhyolite lava is 9 orders of magnitude higher in terms of the viscosity. And by the time you get up to things like granite, you're into the 10 to the 20 Pascal seconds, something like that. The outcrops out on campus here aren't exactly flowing easily. But over millions of years or tens of millions of years, you might be able to detect a small amount of flow of those materials. And the Earth's mantle has more or less got a viscosity somewhere in this range. So there's a big order or big range of orders of magnitude for things like viscosity. And yeah, it's hugely variable. There are other rock properties that don't vary hardly at all, but this is one of the things that really is incredibly variable. So we've seen this equation just on the maybe 2 slides ago, showing this shear stress being related to the viscosity times the strain rate. And this works for what we can call a Newtonian material. So this name will come up in the exercise for today. It just means it's a material that has a linear relationship between stress and strain rate. So this thing is just a constant number right here between the stress and the rate of strain. And there are some good examples of Newtonian fluids like water, air, and thin motor oil. They're basically nearly Newtonian fluids, and but rocks aren't really. So rocks don't deform quite in the same way. And we'll see some examples of why that is, or at least that it isn't the case that rocks are Newtonian later in the lecture. For the moment, we can talk about what happens when you put these kind of viscous fluids into a channel. And so the picture we're looking at here is essentially something like 2 walls that are bounding some fluid in between them. And in this case, you can assume that these walls are sort of infinitely wide in and out of the screen, and that the fluid is trapped in between here. And what we're going to look at is how the fluid flows when you do different things to it. So our first example is one in which I think we're going to move the upper wall of the channel and keep the bottom wall in every case will be fixed. But we're going to move the upper one and say, so the velocity up here for the fluid has to be moving at the same velocity as the wall. So in other words, the fluid is basically stuck to the wall of this channel. And so it's stuck at the bottom and stuck at the top. And in this case, the top wall is moving. This is the general form of some velocity equation that you could use to calculate what the velocity would be of this fluid in the channel. We'll simplify this just a little bit. But these are kind of nice illustrations to get some idea of how these kind of viscous fluids behave. And so one of these end member types of flows is one where there's no pressure gradient in this channel. So in other words, it's not like there's a higher pressure on one side than the other. It's not like if this was a tube of toothpaste, you're not squeezing over here on the one side. The only thing that's happening to the fluid is the top wall is moving. And so that just causes this thing to shear. So the fluid velocity down here is 0 where it's stuck to this wall. It's equal to the velocity of u0 up here where it's stuck to the top wall. And everywhere in between it just increases linearly. And this is called a Couette flow. It's not necessarily something we're going to look at in the examples of what we do today, but these kind of things do occur in nature, and so to talk about the 2 end members, it's useful to see the Couette type of flow, which is mainly driven by movement of one of the sides of the channel. And the equation, if you want to, you can go back to the previous slide, but this is what we had on the previous slide for the velocity of the fluid as a function of its position z. So it's z equals 0 up here and z equals h down there. So the fluid has it's in a channel that's h for the thickness. The general equation looks like this, but if we assume the pressure gradient, this dp dx is 0, then that whole term goes away and you're left with this simple thing that basically just says the fluid velocity will increase in a straight line from one side of the channel to the other. a very simple example. The other end member is called Poiseuille flow, and this occurs when you don't have the walls of the channel moving, so they're both fixed in space, but you apply pressure. So if it's the tube of toothpaste analogy, once again, it'd be like you're squeezing the one end of the toothpaste tube, and then this material is sort of being pushed from the pressure out the end of the toothpaste tube. And so the velocity that you see in this case looks something like this. Now this is an example that we will see in the exercise for today, where we'll look at the example of ice flowing down a channel. And so this is perhaps a little bit more relevant to you for what we'll do today. But essentially, this end member flow says that it occurs when there's no velocity difference between the two walls of the channel. If this is ice flowing down a valley, that makes sense. It's not like one side of the valley is moving. They're both more or less fixed with respect to the ice that's flowing down the channel. But in this case, because the ice is flowing from high elevation downward, there is a pressure that results from gravity that causes the ice to be pushed down the channel. And so you get this kind of velocity profile, so the ice is more or less fixed to the walls. It's not always true, but we can assume in this case the ice would be fixed to the walls of the glacier, or to the valley, and then in the middle of the valley you'd expect to see the highest flow velocity in this kind of simple picture. So those are our end members of flows in a channel, and again, they relate to the exercise today, so that's maybe why it's worthwhile to note this stuff. And in terms of the velocity solution, again, if we had this general equation here for the case where we have fluid flowing in a channel, in this case we said that the velocity of the upper wall, which was u naught before, is equal to 0. So the last two terms drop out and you're left with this thing. And so you can see in here the z squared term, which is why this has the sort of shape of a parabola in terms of the velocity in the channel. And just note here that the coordinate system is a little bit different than the previous case. It's assuming we're using z prime, where we're assuming we're in the middle of the channel, calculating the velocity out from either side. And a nice geological example of this is the way in which salt deforms when you put a bunch of sediment on top of it. It flows like a viscous fluid with nearly linear viscosity. And this is a photo from Nova Scotia in Canada, where you can see the head of a salt diapir that's more or less buoyantly been pushed up toward the surface of the earth and deformed the rock around it. There is an example or an article on the lesson page for this week if you're interested to sort of see how the salt tectonic stuff works. It might be kind of interesting, but it uses both of these kind of end member flow types for channel flow when you talk about salt diapirs, and I think the paper that is posted is a nice way to maybe see one example. You can also apply this kind of viscous flow stuff to magma flowing in the neck of a volcano or something like that, or whatever. So anyway, you can check out the course page for that article if you're curious about that. We have a couple other things we need to talk about these viscous fluids, and when we start talking about thinking of rock as a viscous fluid, I mentioned before that rock doesn't deform like this nice Newtonian way where you have this linear relationship between the stress, or the it's the stress and the strain rate, but rather that rock tends to deform in a non-linear way. And one of the ways in which it's not linear in terms of the viscosity is that rock has a very strong temperature dependence in terms of its bulk viscosity. So this probably makes sense, but as you heat rock up, it tends to flow more and more easily, like most materials you would be familiar with. I mean, if you did the same thing with honey, if you put honey outside on a cold day, it flows much more slowly than if you sort of microwaved it or something like that and it got hot and flows very easily. Rock does the same thing. And that relationship is shown here, where this A naught would be some kind of constant for the rock type that you're looking at. Q is the activation energy for the fluid to flow. R is the gas constant, and T is temperature. And so basically this has an exponential 1 over temperature behavior for the way in which the viscosity is calculated. And so that means as temperature goes up, the viscosity will go down in an exponential way. And I don't know if I have a figure about this, but it doesn't necessarily matter so much for this week's exercise. But it's important to note this is one of the reasons why rock doesn't deform in linear fashion. I guess I do have a figure. All right, I couldn't remember. So here is the example. So if this sigma is another symbol to indicate stress, don't worry about what the D is for right now, but the main thing to see here is that the stress that the rock would experience is quite high at low temperatures, and as temperature increases, the stress needed to make it flow goes down significantly. So this is a more or less exponential shape, and this is essentially how we model the way in which rocks deform inside the interior of the Earth when we include temperature dependence. It's this exponential decrease. And so anyway, that's the picture there. Since it's not so important for today's lesson, I'm not going to, or for the exercise rather, I'm not going to belabor the point here. And we can actually skip over that question. So the other thing is, in terms of nonlinear behavior, that rocks basically don't, at the scale of some parcel of rock, when you deform it, it doesn't deform in a linear way, even if you keep the temperature constant. And what we see is that, for instance, what's stated here, that rock generally will deform about 8 times as quickly when you double the force that you apply to it when it's behaving in a viscous manner. So if it's a linear relationship between stress and strain, if you double the stress, you should double the rate of strain. Here, what we see is that we double the stress and we get about 8 times as rapid deformation. And so this is the reason why we say that rock is nonlinear. There's not a linear relationship between the stress and strain. That mathematically is equivalent to saying this. So now we have the stress over here raised to some power n. And then A effective is taking the place of the viscosity. It's not quite the same. And then we have the strain rate over here. And so this n is the power law exponent, and you're going to look at this in the exercise for this week to look at different power law exponents for ice to see how they change the way in which the ice flows down a valley glacier. And for most rocks, we look at values of n that are somewhere between 2 and 4. So a value of 3 would give you this 8 times as quick deformation when you double the force that's applied. So if you took, this and raised it to the power 3, when you make that twice as big, it makes the strain rate 8 times as large. And as I mentioned here, A effective is similar to the viscosity, but it has different units. It's pascals to the n seconds because, again, we have pascals to the n over here for the stress. So, I don't know, maybe the painful part's over now. We can talk a little bit about glaciers if that makes you feel a bit better. And we'll start with a really simple picture of what a glacier looks like in a valley. So we're looking kind of mountainous glaciers. And essentially we have the zone of snow accumulation up at high elevations and a zone of ablation where down at low elevations we have melting or ice falling off into the seawater if the glacier has reached sea level. And what happens in between is flow of ice from high elevation to low elevation driven by gravity. So if the ice thickness is big enough, the fluid, ice in this case, will begin to shear and flow down toward low elevations. Now, there are basically two different types if you want to classify the glaciers in very broad terms. Cold glaciers that are frozen to the bedrock beneath them, so they'd be frozen stuck to the rock in the valley, or warm-based glaciers where the ice is sliding along the bedrock in the valley. And even this, for a given glacier, may not be entirely cold-based or entirely warm-based. There may be patches that are behaving in one way or another. But this is a general classification, and maybe already something that's a bit familiar to you. Maybe, I don't know. But it matters for the exercise today because if your ice is frozen to the bedrock, that means you can assume that the velocity of ice is 0 at the bedrock interface. And if it's sliding, then you assume that the velocity of the ice is not 0 at the bottom of your glacier. And so your equation that you would use to calculate the velocity of the ice would be a bit different in that case. And in terms of how the glaciers move, well, we've already hinted at one of them, that is basal sliding. So if this is the ice sliding along the bedrock or maybe along some layer of sediment, whatever is the substrate, the material underneath the ice, we've got possibility that the glacier is sliding along. And there's lots of different ways in which that behavior can happen. Water getting trapped underneath the glacier is a really nice way to decouple it from the rock underneath it. But there's also just, depending on the location and temperatures and things like that, you can just have temperatures that are warm enough to cause the ice to slide. The other way, and the thing that we'll look at in more detail in the exercise for today, is internal deformation. So this is flow within the ice, sort of crystalline plastic flow of the material, and it is nonlinear generally for ice, and you'll get a chance to demonstrate that in the exercise. And it's also sensitive to temperature. So like other viscous fluids, if it's really cold, the ice will flow more slowly than if it's close to temperature where ice starts to melt. And what we tend to see is that deformation within the glacier is concentrated close to the bedrock interface, so close to where the bottom of the glacier is or close to the sides of the glacier. So the ice that's within the center is deforming much less than that at the edges. And that probably makes some sense if you've got this fluid flowing down through the valley, that it's going to shear more along the edges than in the middle. So what we're going to look at for the exercise for today is one example is shown here. That's a viscous fluid flowing down some incline. It's a very easy way to relate that to how glaciers would flow, because if you make that viscous fluid ice and you put it in a valley that's got some slope to it, of course it will flow downhill as well. So it's being acted upon by gravity. In this case, we're just calculating the velocity profile without any sliding, but we could include sliding if need be. And what you can see is that the velocity basically goes to 0 at the bottom of the fluid, and it increases as you go up the column toward the free surface, or toward the surface of the ice or whatever the fluid is. And so we're going to look at the flow of ice in this kind of view, so flowing down an incline, and we're also going to look in kind of a map view of ice flowing between two walls of a valley. So that's more like the channel flow thing that we saw. And so you'll calculate basically these kind of velocity profiles for different thicknesses of ice and then compare it to some observations. So that's what's coming in the exercise, and I think that's essentially it. So just a quick recap of what we covered. Talked about viscous flow briefly, mainly tried to focus on stuff so you'd be prepared to have some idea what's going on with the exercise today. We can go into a lot more detail about this and talk about why rocks deform in a nonlinear way, but that's perhaps for another course. And the general idea is that rocks and ice both do deform in a viscous way in certain conditions and at certain time scales. The general relationship is, for any viscous flow, is one in which we have deformation rate being proportional to the stress that you apply to the fluid. We saw these end-member viscous flows, the Couette type flow, where you have this linear increase in velocity from bottom to the top of the channel, and the Poiseuille flow, it's more like a parabolic shape of flow within the channel, and that those reflect differences in the velocities at the boundaries of the fluid, so movement of the walls of the channel or changes in pressure along the length of the channel, and that these things can be mixed. Those are the end members, but in natural examples you can observe both behaviors in the same fluid, and the salt tectonics paper on the website might be useful if you're curious about that. And then lastly, we talked about this idea that rocks are not going to deform in a linear viscous way, but tend to be nonlinear, not only because of the effects of temperature, but also because of the things that happen at the atomic scale in crystals and how they deform. And you get this sort of different deformation mechanisms happening at the crystal scale that cause the rock to do things like deform 8 times as quickly when you double the stress that you apply. I think that's it for this part. So lecture slides are up on the site. You can take a look at those if you want to refresh your memory at some point. And we'll move here, just take a quick look at the other stuff that's in the lesson, and then a preview of the exercise. So I'm just going to do this, and I guess hopefully you can see that all right. Here's the paper that I mentioned about salt tectonic stuff. There's a link to it here. You're welcome to take a look at that. There are some notes, as usual, about the viscous flow down an incline. And like the previous weeks, if you want to understand a little bit more of the math that we use in the exercise and where it comes from, you can read through these notes. It starts in quite a general framework, which is from potential energy, looking at the difference in potential energy for some fluid at one position and at another position, and why it flows down, and the stresses that are generated within the fluid as it flows. So that might be of interest to you to read through that. You don't necessarily need this part for the exercise today, but it might be, again, helpful as a supplement. Maybe we could say it that way. But if we go to the next part, there is a section in the exercise for this week called Theory for Exercise 12. It's the next thing in the lesson, and you will need a bit of this. You don't necessarily need to read through and understand every one of the equations and how they go from one to the next. I wouldn't mind if you did that, but it's not absolutely necessary. But you will see in the exercises this week references to this part of the lesson where it'll say, go back and use this equation from the theory for the lesson for this week. There are, I think, 19 equations in here, and you're going to be referred at least to this number 19, to number 12, and number 11, and I think also to maybe number 9. Anyway, you'll see references in the text. When those references are referring to a certain number, it's referring to this number in parentheses after the equation. So those are the equation numbers. I've also put some notes in places to kind of show what happens from step to step in here in the theory. If you kind of just maybe don't see what happens from one step to the next, I've tried to say what's different in places. But this goes through the examples of first a channel flow, so ice flowing between two walls that are fixed, and then how you calculate the velocity of the ice as it flows through this channel. And so you can read through the equations there. I'm not going to go through this in detail because it's not really that interesting to do as a lecture, but it's maybe more interesting for you to read through. And so that's the first example, and you'll end up plotting this equation number 12 in the first part of the exercise for today. And maybe just to make a point, it has some, I don't know, something that is probably quite familiar to anyone who's a bit mathematical in their thinking, but unfamiliar to a lot of people. Things like non-dimensional velocity, which is a velocity that does not have any units. What that means in this case is that we take the velocity we would calculate and then we divide by the mean velocity of flow in the channel. And what it allows you to do is look at the pattern of, or the shape of the velocity rather than the absolute values of the fluid. But if you take something that is in meters per second, for instance, and divide it by meters per second, of course you have no units there. So that's what this non-dimensional velocity refers to. So for u, when you calculate this equation 12, you don't need to calculate u and u bar separately. This is just one term in terms of what you would calculate in Python. It'd be one variable is equal to this stuff on the right side. And we can gladly provide a little bit more explanation if that's helpful. The second part is for problem 2 in the exercise where we look at ice flowing down some slope, and this walks you through how to calculate the velocity of the ice as it flows down the slope. And I think the picture sort of summarizes here what you're going to end up doing, and that is to calculate these kind of velocity profiles. So that theory section will be important for the exercise. Again, you don't need to read and understand every single thing there, but you'll get referred back to that several times in the exercise, so be prepared for that. All right, so let's just take a quick look then at the exercise itself, and then I'll turn you loose to get started. So here we have exercise 12, and the first part is looking at flow of ice in a channel. And so you have a starter script here, and you're going to fill in some things to get the starter script working, including putting in the equation that you need to use to calculate the velocity. And probably the trickiest thing in this problem is the equation will work nicely for values of the width of the glacier that are positive, but you're asked to make a plot for the for a symmetric system. So we want to have from one wall on one side to the other wall on the other side, and when you go to the one side you're going to have negative numbers for the distance, and that will, as you see when you get the equation in there, will make some weird things in your plot, and you have to deal with that, making some minor change in equation 12 for certain cases. Yorina and I will be able to help with that when you get there. It won't really make much sense until you get to that point, but when you get to the point that you've put in equation 12 and you start seeing things that don't look quite right for the velocities, we'll help you out. Otherwise, you know, it's I think standard stuff in terms of the starter script and filling in some values. I've tried to put in a few more things than I have in years past, so there's a little bit more structure there, and hopefully that helps get you pointed in the right direction. The second part of the first problem is looking at an example of a glacier in Canada, in Alberta, called the Saskatchewan Glacier, and here we have some observations of the velocity of the flow of the glacier as you go from one side of the glacier to the other. And so what you're going to do is calculate the velocities with your code for viscous flow in a channel and then compare it to these observed values going across the glacier from one side to the other. So you'll load in a data file that has this data and plot that and then compare when you do the same calculation for your model. How well does it fit the data? And there are a couple questions about that. Second part's where we look at ice flowing down an inclined plane, and we've already kind of hinted at that. Looking at another glacier, I think it's actually in the same ice field in Canada. So this is the Athabasca Glacier, the picture of it shown here. And again, we've got observations from the bottom of the glacier up to the top, in this case, of the velocity of flow. And you'll calculate these velocity profiles of the ice going down this incline and then compare that to the observed values from this glacier in Canada. You've got a starter script again for this one, and same kind of thing as the first exercise in terms of putting in the equation and working with it. So yeah, that's the exercise. And are there any questions? No. So as usual, you guys can go ahead and get started, and we'll be here to answer questions. I will make note of one thing here, that there are already a couple hints for this exercise that are up. You're going to be asked to calculate these values of, in this case, this P1 minus P0 over L, or in problem 2, this thing called gamma x. These are the values you should get for different values of n. So the n is this power law exponent, and this will allow you just to see whether your calculation of P1 minus P0 over L is right or not. Students last year were having a hard time knowing whether or not they were getting the right answer, so they asked that this be made available, and I think it doesn't really, well, it would be very obvious to Yorina if you just copied and pasted these values into your code. So I think, you know, if you want to just check whether you're getting the right calculation, the numbers are here in the hints. If there are other things that come up in the hints during our discussions, I'll try to post those, or if there are questions on Slack or whatever, I'll put more stuff in the hints as needed. So for now, feel free to go ahead and start, and we'll be here to answer questions and do stuff like that.